Hello everyone again. So I'm gonna continue with lecture 3. And before doing that, so let's make a quick reminder of what we did yesterday, lectures 1 and 2. So yesterday we checked that the class of self-similar processes is that of scaling limits. Okay? Meaning that every process that is self-similar can be obtained as a scaling limit of a sequence of stochastic processes. Okay? And that the scaling is always of regular variation. Okay? And also, we state an important theorem that we are going to prove today, which is Lamperti's theorem, or Lamperti's representation, which says that every positive, so positive in the sense that it only takes positive values, positive self-similar Markov process can be seen as the exponential of a Lévy process time change. Okay, and I'm gonna make that more precise. Okay, so I'm gonna explain explicit this transformation. I'm gonna prove the theorem, but to do that, let me remind a couple of definitions, just to make sure we are all speaking about the same thing. So remember, self-similar Markov processes are self-similar and strongly Markovian processes. Okay, and what do I mean by strongly Markovian? We will say that a process xt for t positive, okay, which is rd valued, okay, defined on a space omega f with a filtration. By a filtration, I mean an increasing family of sigma algebras, okay, and a family of probabilities, px for x in Rd, okay. It has the strong Markov property okay, if for every stopping time for t of the filtration ft, that means that the event t is more or equal than t is in ft for all t positive. Okay, we have that the law of the process xt plus t for t positive conditionally on ft cap intersection t being finite. Okay, so this is the filtration up to the random time t, capital T. It has the same law as xt for t positive, okay, starting from the random position xt. Okay, so the position of the process at time capital T. Okay, just should I remind what ft is? Ft is a family of sets in F such that the event A intersection T is more or equal than T is in Ft for all T positive. I mean, this is just something technical, but just to have the right notation, okay? And to check this, it is in fact to verify that for every x in Rd and f from Rd into R, let's say measurable and bounded, we have that the expected value starting from little x of the process at time xt plus s, given what has happened up to time capital T, is just equal to the expected value taken at the position C of f of xs when C takes a value xt, okay, and this also for every s positive, okay. In particular, x is a time homogeneous Markov process. Okay. So I hope everybody is familiar with this definition, but if not, we can just take it as granted, and this will be very useful later. Okay. So all our processes are time homogeneous. They have this strong Markov property, okay, so that the property of the present and the past are independent conditionally. The past and the future are independent conditionally on the present, even if the present happens at a random time, okay? So this time is the time of the present, where we observe the process, and we observe the future and the past, and these two events are independent, okay? We will also, just for technical reasons, we assume also that x has right continuous and left limited paths, or in the French notation, we had cat-lag paths, okay, and also that X is what is called quasi-left continuous, meaning that if Tn is a sequence of stopping times drawing to T as n goes to infinity, then xtn will converge almost surely as n goes to infinity to xt on the event where t is finite. Okay? It's just meaning essentially that x, even though it has right continuous and left limited paths, if you fix a time t, okay, essentially you will see something that is a bit of the path that is continuous. Okay? This is something technical that is also needed. Okay. The strong Markov property for Lévy processes can be written in the following way. Okay. This condition that I wrote here, all the conditions are conditions that are satisfied for Lévy processes. Okay? But a way to write the Markov property, the strong Markov property for Lévy processes is that if psi is a Lévy process with respect to a filtration in a space omega f ft and some probability p, okay, and t is an stopping time in this filtration, okay, then psi t plus s minus psi t, so the increment at time from capital T to capital T plus s is independent of what has happened in the process up to time t, and this holds for every s positive, okay, on the event where t is finite. Okay. So this is just saying that the property of independent and stationary increments of the Lévy process is preserved when we take random times. Okay, and there is something else, and has the same law as psi s for s positive. Okay. This is just another way to define Lévy processes, if you recall that. So for Lévy processes, a way to define Lévy processes is that this holds for a fixed time, for any fixed time t. Okay. And the strong Markov property for Lévy processes means that we can change that fixed time t by a random time, by any random time that is a stopping time. Okay?
The independence and the identical property holds on the event that t is finite.
Yes.
So maybe he's meaning, you are meaning consider the conditional probability.
Yeah, yeah,
Event.
so, yeah, on that event, yeah. Mhm. Yes. Mhm. Yeah, so you take the expected value of an event of this and the expected value of an event of this. Indicator t is finite, and you prove that that is equal to the expected value of this indicator t is finite times the expected value of this. Sorry, the expected value of this. Of that event defined in terms of this. Meaning that the expected value of any psi t plus s minus psi t for s positive. This is any test function, and any test function g of psi u for u is more or equal than t. This is equal to the expected value of f of psi s for s positive times the expected value of g of psi u for u is smaller than capital T, indicator t is finite. For every f, g measurable functionals. That's the meaning of this notion. Okay. For those of you who are not familiar with random times or stopping times, just think that this is allowing you to treat random times as fixed times. Okay? It's a bit an abuse of notation, but let's think of that. Okay? And why this is important? Because in the Lamperti transformation, or the Lamperti representation, we're observing Lévy processes at random times. Okay, so I need this kind of formality. Okay. Well. Okay, so I'm gonna give some details of the proof of the Lamperti representation. Okay. But before, I want to know if there is a question, or there is any question about this. Is it okay? So, what did Lamperti representation says? Okay. It tells us that if psi is a killed Lévy process, taking values in R union minus infinity being an absorbing time, okay, then the process x defined as x times exponential psi tau t x to the minus alpha when t is smaller than x to the alpha, the integral from 0 to infinity exponential alpha psi s ds, and being equal to 0 when t is above than x to the alpha 0 infinity exponential alpha psi s ds, and this holding for all t positive and x positive, then x is a 1 over alpha positive self-similar Markov process. Okay. Killed at 0. And with a lifetime t0 that has the same law as this random variable that is here. Okay. Then this is for each alpha in R. Okay. So verifying this claim is rather easy in the following sense. So you can, from this construction, you can easily check that x so defined, okay, has the scaling property. Okay. So
you exclude the case of alpha equal to 0.
Okay. Yes, okay. Just I write 1 over alpha when alpha is different from 0, but yeah, when for alpha in R, so yes, let's say alpha different from 0, okay? But if alpha is equal to 0, the definition is still right, just the notation is not correct. Okay? So, but the construction is valid if alpha is equal to 0. Yeah? It's just the exponential of the Lévy, in fact. Because if you take alpha equal to 0, this is just, this is 1. Okay, so there is no time change other than x to the minus alpha. Yeah? Mm-hmm. So so we can just check that it has the scaling property. So indeed, for any C strictly positive, the process xt c times x times x c to the minus alpha c, okay, when t is bigger or equal than 0, is equal to c times x, the exponential psi, in the time t times x times c to the minus alpha for t positive, okay? But this, by construction, is just xt c times x for t positive, okay? So these processes that we build here has the scaling property. Okay. Well, in fact, okay, here I should be more careful I should be writing t is smaller or equal than c to the alpha times t0, the first heating time of 0. Same here. And here. Okay. But it doesn't change anything because after, when I put 0, it's equal to 0 everywhere. Okay. Okay, so it has a scaling property. Now we need to check it has a strong Markov property. But I will not do it. For that, I'm going to quote a result that is due to Volkonsky that says the following. Volkonsky. This result, you can read it in the book of Karatsas and Shrif. Okay. The theorem reads as follows. So take AT to be defined as the integral from 0 to t of a function v of yu du, okay, with v a measurable function and positive, such that the integral is finite. Okay. Yeah. For all t. Okay. Positive. And y a strong Markov process. Okay. And define Ct to be the inverse of this additive functional. Okay, this for every t positive. Okay. Then the process y tilde defined by time change has y tilde of t is equal to y at ct if ct is finite, and as the symmetry state, if for y tilde, if ct is infinite. Okay, so remember ct is infinite when the infimum, when the set is empty. Okay. Then this process for t positive has a strong Markov property. This process has the strong Markov property with respect to the filtration f tilde of ct okay, so for each ct is a stopping time. Okay. So you take ct, where is that? Okay. Here it is. There. Okay, so you replace capital T by ct for each filtration. Okay, and this is the a new filtration for this new process, and this process will have the Markov property with respect to that guy. Okay. And what else? We also have that. Okay, I'm not being totally accurate, but so Y has a strong Markov property with respect to the filtration, to a filtration ft for t positive. Okay, that filtration I transform it, I time change it with respect to c, and I get a new process that has still the strong Markov property. Okay, so this is just telling us that that the strong Markov property is preserved under time changes. Okay? And there are many other nice properties, as for instance, this guy is adapted with respect to this guy, stopping times with respect to this guy become stopping times with respect to this guy, and so on. Okay? But we don't need to use that at the moment. But we need to know that this guy is still a Markov process. Okay? So if we take that for granted, then this guy that we just built, where is it? Here. Okay? It has a Markov property, the strong Markov property, in fact, and it has a scaling property. So we can be calm, relax. This process is a positive self-similar Markov process. Okay? Is there any question about that? Yeah. Oh, fct. This is yeah. F tilde of t is fct. Thank you. Yeah. Okay. Okay, so now let me prove that if we start with a self-similar process, then we find a Lévy process by this transformation. Okay? And I want to do that with some details because it helps to get acquainted with this notation and with this formality. given a positive self-similar Markov process X that is killed at 0, so the first time it hits 0, then the process psi defined by psi t, which is given by the log of x of bt over x0 for t is smaller than the integral from 0 to t0 of xs to the minus alpha ds. So remember, t0 is the first heating time of 0 for x, and as minus infinity if t is bigger or equal than the integral from 0 to t0 of xs to the minus alpha ds. Okay? This process for t positive is a Lévy process that takes values in R union minus infinity with a lifetime zeta, which has the same law as the integral from 0 to t0 of xs to the minus alpha ds, and follows an exponential distribution of parameter q for q bigger or equal than 0. Okay? And that yesterday I used the notation exponential q. Okay? Okay. And also here the definition psi does not depend on x0. Okay. And we also saw three properties, C1 to C3 hold. Okay, so remember is that either the process never hits 0, or it hits 0 in a finite time and it does it continuously, or it hits 0 in a finite time and it does it by a jump. Okay? And that is related to the behavior of psi. Okay? Okay. Okay. So, if I apply the Bolkonsky theorem to this process, yes?
Did you define BP?
I didn't. Thank you. Bt is the inverse of the integral from 0 to s of x u to the minus alpha du being bigger than t for all t positive. Okay? And as before, the infimum of the empty set is plus infinity. Thank you. Okay. Okay. So if I define this process like that, and I apply Bolkonsky theorem, I immediately have that this process has a strong Markov property, okay, and that it takes values in this set, okay. But I still need to check that it has a property of independent and stationary increments, okay. And there is where we need a little bit more of work, but it's not too much. But before doing that, let me check the conditions C1 and C2 to C3. Okay. So C1 tell us, well, in fact, yeah, okay, part of it. So let me check that Px of T0 is finite, is equal. So let me check this. So claim is that Px of T0 is equal to 1 for all x positive, or is equal to 0 for all x positive. Okay. 2 is that Px of T0 is finite, and xt0 from the left is equal to 0. Is the same, is equal to 1 for all x positive, or is 0 for all x positive. And the third possibility is that Px of T0 is finite, and xt0 from the left is bigger than 0. This is again equal to 1 for all x positive, or 0 for all x positive. So let's make the proof. So take xx be a positive self-similar Markov process issued from little x, okay, and for C positive, take x tilde of x to be the process C times x tilde t c to the minus alpha, starting from x divided by c, okay, for t positive. Okay, so x tilde has the same law as x just by the scaling property. Okay. And what about the first heating time of 0 for x tilde? The same heating, the first heating time of 0 for x tilde should have the same law as as c to the alpha t0. Okay. Is that clear? Because this is the first time where c times this is from xc. Okay. Sorry, this is starting from x. This guy is starting from x, and this is for the first heating time of 0 of the process starting from x divided by c. So it's the same. If you do that, this is just equal to c to the alpha, the infimum of t positive, where x divided by c is equal to 0 for t. Okay? This is c alpha t0. Okay? from this property, okay, we check that if the pro starting from x is finite, that happens if the pro starting from x divided by c is finite, okay, and vice versa. So this probability that is here does not depend on x, okay. So T0 being finite does not depend on the starting point. Okay. So let's call P the probability starting from any point x for T0 being finite. Is that okay? Is there any question about this identity here? No? Okay. Okay. So this is a constant. This is a function that is constant on x because of the way of this argument that is here. Yeah. Okay. I must have said that I put the depends on the starting point here. But then I remove it because it doesn't really depend in some places. Okay. Okay, so I call P the probability starting from some little x for T0 being finite. Okay. This doesn't depend on x because this is a constant. Okay. Then by the Markov property, we have that the probability starting from x and t being smaller than T0 and T0 being finite is just, if I condition on what has happened up to time t, I apply the Markov property, I get that this is equal to the expected value of the probability starting from xt, the position where I am at time t, of T0 being finite, and here I still have the event t is smaller than T0. Okay? But again, this is a constant, so this is equal to P times the probability starting from x for t being smaller than T0. Notice that this function that is here is a function of t and of x. Okay? It will depend on x because there will be an x to the alpha appearing somewhere. Okay? So this function is not a constant of x. So if we use that, we have that P, which is the probability starting from x for T0 being finite. This is equal to the probability starting from x for T0 being smaller or equal than t plus P times the probability starting from x for t being smaller than T0. Okay? I just apply this identity here. Okay? But this is equal to Px t0 is more or equal than t plus p times y minus 1 minus px, t0 is more or equal than t. Okay? And so we get that p is equal to 1 minus p times px for t0 is more or equal than t times plus p. Okay? So we can get rid of these two guys, and so we get that 0 is equal to 1 minus p times px of t0 is more or equal than t. Okay? And when we make t go to infinity, this goes to 1 minus p px of t0 being finite. Okay? So p times 1 minus p should be equal to 0. Okay? So this is proving this. Yeah, it's just using this, which is a consequence of the Markov property. Then we split the event t0 being finite as t0 being smaller than t or bigger than t. Okay. Yeah. And then we use that this can be written. Yes, no, that's right. That was correct. That was correct. That was correct. Yeah. Okay. Okay, so this p should be equal to 1 or to 0. Okay, it's a 0-1 law. Okay. Let me now prove the second. So, again, by a similar argument, we have that the function px for t0 being finite and x t0 being equal to 0 is a constant for all x positive. Just do the same. Do the same as in here. Define this process x tilde. Okay? And because we are determining the event where x t0 minus is equal to 0, we will see that this doesn't depend on x. Okay? Just by doing the same trick of writing x tilde of x in this form. Okay? Yeah. Should I write it? I mean, this is just px of t0 tilde being finite and x tilde t0 tilde minus being equal to 0, which is equal to the probability starting from xc, from c c alpha t0 being finite and c x t0 being equal to 0. Okay, just by doing the same trick. Okay? If I do exactly the same trick, I get rid of the dependence. Of x. Okay. So it is a constant. Okay. So let's call ky minus to be the first time where xt is smaller than y. Okay? I will take ky minus to be equal to t0 if the set where xt is smaller than y is equal to the empty set. Okay? Okay. So we have that p is equal to the probability starting from x for t0 being finite and xt0 minus being equal to 0. Okay? So if we are below, if we hit 0, then we are below any level y. Okay? So this is equal to the expected value starting from x for the indicator ky minus being smaller than t0 being finite, and xt indicator xt0 minus being equal to 0. But we apply the Markov property at the time ky. Okay, so this is equal to the expected value starting from x, indicator ky minus is finite, and then the probability starting at xky minus of t0 being finite and xt0 minus being 0. Okay? This is not very... Let me write it again. So this is the expected value, indicator ky minus is smaller than t0, and the expected value, or the probability, starting at xky minus of t0 being finite and xt0 minus being equal to 0. But this is just the Markov property, the strong Markov property at the random time, ky minus. Okay? This is a constant, again. And so we just get that this is equal to p times the probability of this event, starting from x. So p equals to p times the probability of ky minus being smaller than t0. Okay? And this happens for all y smaller than the starting point. Okay? So here we have that either p is equal to 0, okay, or p is bigger than 0. This is one of the things we wanted to prove. Or if it is bigger than 0, then 1 should be equal to px ky minus smaller than t0 for all y smaller than x. Okay? So the probability that we hit a level below y before hitting 0 is equal to 1. Okay? So thus x goes below any level y, okay, and with probability 1. Okay. And this ky minus, okay, is smaller or equal than t0, but in fact ky minus will grow to t0, okay, because we are going below any level y, so eventually we will hit 0. So we are getting closer and closer to 0, okay. And by the quasi-left continuity, and here is where it is important, we have that x ky minus will converge to x t0 minus. Okay? But all these events are of probability 1. Okay? So this event is of probability 1. Okay? So P is equal to 1. Okay? See, if it is strictly positive, then it is equal to 1. Okay. So this proves the second claim, and we are left to prove the third claim. Yeah, but it's no, that's it. Because with the other two guys, by the scaling property, okay, by the scaling property we have that this doesn't depend on x, okay, and because the complement of this is this event, if this is bigger than, this is 1, then this is 0, okay. So that finished the proof of this term, of this part. Okay, let me now write the proof of the independence of the increments. Where is it? Is there any question about this? Is it okay? Okay, now I can delete this and okay, so now we need to verify that for any Ts positive on the event where T plus S is smaller than the lifetime, so C is the lifetime of psi, okay. The process psi T plus S, as we define it, minus psi T, is independent of ft, okay, where ft is, remember, the filtration, so let's say g of bt, where g is the filtration of x. Okay? So it's just what has happened on x up to time bt. Okay? Okay. So bt is just the inverse of the, so remember bt is the inverse of the integral from 0 to s xu to the minus alpha du bigger than t. Okay? So this bt has the following property. Okay, so we want to prove this fact. Okay, so to do that, observe that bt plus s is equal to bt plus the infimum. So to be above level t plus s, I should be first above level t, and then pass above the remaining space. Okay, so plus the infimum for u for r positive of the integral from 0 to r of x u plus bt du bigger than s. Okay, what did I do that there? I wrote the integral from 0 to s as the integral from 0 to bt and from bt to s. Okay? So here to do that, to get that, I wrote bt plus s to be the infimum of s positive from 0 to bt from u x l minus alpha dl plus bt plus u xl to the minus alpha dl bigger than t plus s. Okay? But this guy that we have here is just t. Okay? And then here I make a change of variables. R equal to L plus bt. Okay? And by doing that, I get this identity that is here. Okay? So I will get, if I do that, I get and then I make a change of variables b equal to u plus bt here, and then I get this bt here. Okay? Just to make this a bit clearer. Okay? Okay, but this guy that we have here is just bt plus s for the path starting at the position bt. So this is just the shift operator. So this is just telling me, observe the path of x from bt. Okay. And also, So just to determine, if I know what has happened up to time bt, I know this random variable, okay? And I need to observe the remaining of the path of x, okay? But the remaining of the path of x from the bt, okay, is again a copy of x, okay, but starting at the position that I reach at time bt. It's just a Markov property, okay? So, by the strong Markov property, at bt, we have that the law of the process x at bt plus u for u positive, given what has happened up to time bt, okay, is equal to that of this process starting from this point x at bt, which is the same as that of x u times c to the minus alpha times c for u positive, with c equal to bt, xbt, sorry. Remember that starting from a position little x is the same as multiplying the process by little x or by little c, okay, and time changing by c to the minus half. Okay, so recall that x starting from little x has the same law as x times x to the minus alpha point, okay? Starting from little x is just changing the scale of a space, okay? But this guy that is here, tilde, x tilde, is independent of x bt, okay? In fact, we can take it as a process starting from 1, okay? So it doesn't depend on the starting point. The dependence on the starting point of this process is via the time change. Is that correct? This is one of the most important points, I will say, of today. Is everyone okay with this? It's just applying the Markov property. So when I apply the Markov property, I observe the same process, but starting at the position xbt. Starting at xbt because of the self-similarity is just multiplying by the starting point a process that starts from 1. Yes? But doing a time change. Yes? Okay. Okay. So take ht, which is ft, which is gbt measurable, and positive. Okay? I want to prove that the expected value of this ht times the exponential of I lambda psi t plus s minus psi t on the event when t plus s is smaller than c, okay, this is equal to the expected value of ht in the event when t is smaller than c times the expected value of exponential I lambda psi s indicator s is smaller than c. As I said before, this is just like proving the independence of the increments and the stationarity of the process I. Okay, this is what I wrote just at the very beginning of the lecture. Okay, if I can prove that, then everything will be done. This is starting, in any case, from 1. Okay. I take 3 or 4 more minutes to finish this. So, just by construction of this guy, this is equal to the expected value of ht of bx at time bt plus s of x bt to the power I lambda, the indicator t plus s is smaller than the lifetime. Okay, so if t plus s is smaller than the lifetime, this bt plus s is well defined, is finite. Okay, so I condition with respect to the filtration up to time bt. So this guy goes out of the expected value. So we have this is conditional on f on gbt, okay, because this ht is measurable with respect to this guy. Okay. Then by this, okay, this bt plus s is coming from what is seen up to time t, and then what is seen in the future, okay, and this is also what is appearing in the future. So this by the Markov property is ht indicator t is smaller than c, and then the expected value starting from x bt of x bs over x0 to the I lambda indicator s is smaller than c. Yeah? So remember, x time change has the strong Markov property. Okay. X time change has a strong Markov property. Okay. So when I apply the Markov, when I condition with respect to the past, I get a copy of the original process. Okay. In the remaining time, which is s. Okay. It's just the Markov property. This equality is due to the Markov property. And this here. Okay. So this is equal to the expected value of ht, indicator t is finite, and then the expected value of xbt of exponential I lambda psi s indicator s is smaller than c. Okay? But how is the dependence on this point? There is in fact no dependence in the definition of psi. There is no dependence on this guy. Okay? Psi does not depend on x0. Okay? I will prove that. This is just equal to ht indicator t is smaller than c. Okay? And this is what we wanted to prove. Okay. Maybe I can leave this as an exercise or I can prove it, but it's just, again, introducing x tilde x as c times x c to the minus alpha t x divided by c. Okay. Try to do this as an exercise for tomorrow, and we discuss this tomorrow. But it's really not difficult once we introduce again this kind of trick. Okay. So let's make a break for the moment, and then we continue after the break. But you can ask questions if you have questions now.